Started with a quick recap where we are today with containers and Kubernetes and Google Container Engine. Oh, something went wrong. Well, actually, this isn't a real outage, luckily. But for the software developers in the room, I have some good news for you. It's not usually your code that is the main cause of outages. It's actually the way it's configured, operated, deployed. So operating software is difficult. We have all of these things to think about. So how do we deploy our software? How do we deal with continuous integration? How do we deal with scaling? How do we deal with monitoring without fear? How do our services discover each other so that they can communicate? Well, let's see if containers have some of the answers. Containers give us a consistent, portable packaging format. So we have somewhere where we can wrap up our application code and our dependencies together. It's mutable, it's immutable, it can be versioned, we can stash it in a container registry. It's a really handy artifact that makes it easy to deploy. And most importantly, it can run anywhere. So Docker has become the de facto container runtime, and it will run on pretty much any OS. We get lightweight isolation, which means we can disentangle our application processes from each other. They won't stomp on each other's application code and dependencies. Libraries can be managed independently, application by application. And we can set restrictions on how much CPU and memory each of our applications get to stop them from competing with each other. And this is all really lightweight. So unlike a VM where you might have a hypervisor and a guest OS, these restrictions are enforced by the kernel, which means they can start up and stop really quickly. And they're kind of transient processes aside from any data they might store. And also we have a standard control plane. So no matter what we're running and where we're running it, we can stop it, we can start it in the same way. We have hooks into monitoring. But does that get all the way there? I think we still have to think about all of these things. So which virtual machine is our container going to run on? How are we going to replicate it for fault tolerance? How will we know if it's healthy? How will we handle incoming network traffic, load balancing, things like that? How are we going to wire up our applications so that they can speak to each other? And then there's microservices, which means, if you're decomposing your monolith or your larger service into lots of little services, you have all the more to think about, and you have all of these extra communication paths that suddenly appear. So you have amazing complexities potentially to deal with there. Well, that takes us to Kubernetes, and I think it has answers to these questions for us. So at its root, Kubernetes allows us to schedule and run containers on a fleet of physical machines or virtual machines. And it allows us to cut the cord with the physical world. So we don't have to think anymore about where our applications are running. Instead, we can think about things in terms of an application or even a service-centric view of the world. Kubernetes was initially developed inside Google. I think we first announced it about 3 years ago, and it went 1.0 about 2 years ago. And at that time, when it went 1.0, over a quarter of the code had come from outside of Google. It shows the larger community was involved from the beginning. And in subsequent releases, more than half of the code has come from the wider community. So I think you can see that community and the general software development community and operations is now the power that's driving forward the state of the art with this framework. And the community is enormous. I think there was a Tech Republic article a while ago that showed that the Kubernetes community is something like 5 times larger than the nearest similar community. So Google has now 7 apps, I think, which operate with more than 1 billion active users. At Google, we believe that running applications in containers is the right place to do it. And we've been doing it ourselves for 12 years. And I think you can think pretty much any one of those services that's serving those users, maps, whatever, is running inside a container. Now, all of this story with Kubernetes doesn't mean that your ops team is going to be out of the job. The Google ops team, the core ops teams continue to grow. But the number of containers in our fleet has grown over 10 times faster. So, to tell us a bit about Kubernetes in the wild, I'm really excited to invite our friend from Excite to the stage. So please give Higo a round of applause, and he's going to tell us.
Hello, guys. Thank you, James. Thank you all for coming. It's great to be here today to talk a bit about Excite, Kubernetes, and Google Cloud Platform with UI. For starting, what we do at Excite? Well, Excite is a personalized music television channel. You could see it as Spotify or Netflix for music videos. And our application, it runs on top of our linear channel. And based on what our users decide, like keep, skip, or like one music, we keep doing indications for them, recommendations on real time. And we have now more than 100K music videos in our database, and this amount only grows each day. Yeah, this is how the application looks like. On your TV, you can have different kind of channels, like just rock music, or you can really personalize it. And depending on the actions, like this is what looks like on your TV. When a user likes a video, this is what it looks like when he or she skips it. Of course, you can watch straight away on your TV. And based on the actions that the user just took, our algorithm improves the video recommendation in real time. As you can see now, we are improving that channel. So it's actually a very cool thing to run and to maintain. And if you want to test that by yourself, we invite you all to go to Zigo, if you have, channel 25. This is nice. OK, now let's go to the cool part, coolest. When I first started at Excite, I found this infra running on premises and encoding video on Mac Minis. As you can imagine, a lot of things could go wrong there, and it did. So we had all kinds of outages, like crashing servers, limited storage capacity, power, electricity power. Sometimes we had electric power on our building, then we need to send the entire music department home because they could not work. And of course, one of the main problems also, the solution on premises was not scalable at all. If we need to encode more videos, then we need to add more Mac Minis and keep maintaining it. So this was like not good. So the first thing that came to my mind when I arrived was, not in hell I'm keeping any of this. We are going to rebuild everything. And about this new platform that we would start, well, I knew 3 things for sure about it. First of all, it had to be cloud agnostic. Because at Excite, it's very important for us to be sure that our users they are being provided, have been provided with the best service possible we can offer to them. And we do believe that to be able to choose in which cloud platform we are going to run our solution, it's an essential part on this process. So the platform, the solution, the new one, had to be cloud agnostic. And of course, open source community had to be behind it, because we do know how important the open source community is for any project. And great news James just gave us, that now more than 50% of the code of Kubernetes, they came from the community. And another important fact about this new platform was that I wanted it to be fast and efficient. Fast at the point that we could reply all API requests in like small milliseconds, and efficient at the point that we can encode 4K videos cheap, in an affordable way. So after analyzing these 3 conditions, these 3 main conditions, it was clear that Kubernetes would be a great choice for us, and we went for it. Okay. After we decide going for Kubernetes, why to go for Google Container Engine? If you don't know, Google Container Engine is the Google solution for hosting containers. Well, so why going for it and not going to any other cloud provider? As you know, Kubernetes can run in multiple different places. Well, the first reason why we decided going for Google Container Engine was the fact that it's already itself a Kubernetes cluster, which means the container engine itself is already running inside Kubernetes. And this is a pretty cool thing, and also proves that the technology works. After that, another important point on choosing Google Container Engine platform was the fact that there Google can manage the Kubernetes cluster, for the Kubernetes master for you. And this saves a long amount of time. Instead of managing the master, updating it, I just let this job to Google, and I keep focused on making the cluster better. And this is like a huge, huge advantage. And another thing that we went for Google Container Engine is the cost benefit. They have all kinds of discounts. If you keep your server running for the full month, all the weeks of the days of the month, you get immediately a sustained use discount on your VM, which can be around 30% of its price. So it's actually a very good cost efficient. So we decided to enter for Kubernetes, then Google Container Engine, and this was a good choice. So I will talk you now how we do encoding videos on Kubernetes and Google Container Engine. Actually, our encoding process, it's very efficient. Every time we need to encode a new video, Kubernetes starts a pod, an encoding pod, on a preemptible VM, 32 vCPUs, and the only job of this pod is to encode that specific video. When it's done, Kubernetes will automatically destroy the pod and also the preemptible VM. If you don't know what a preemptible VM is, well, a good way to explain this is more like an excess of computing resources on that specific Google data center. So Google is not in use at that moment, so Google offers you to have a VM as a preemptible, which means that this VM is going to run up to 24 hours. However, it can be destroyed by end time by Google, which is just 30 seconds notice, if this excess of computing resources is needed somewhere else in the data center. However, they can cost up to 80% cheaper than a regular VM. So it's actually a good deal. You can see a preemptible VM as a beautiful butterfly. It's going to arrive to your life fast, make it better, bright, and suddenly, this is out. So your application also has to be able to handle it in case of a resilient problem happens because the preemptible machine was destroyed. However, this works pretty good for us. And this is one proof of that the integration between Kubernetes and Google Cloud Platform works great. We use Kubernetes node selector to define on which node pool that specific pod should start. A node pool, it's a Google Container Computer Engine feature. It allows you to deploy several different groups of machines that contain the same hardware on it. And it's a very nice feature because in our case, we can have a node pool with 32 vCPUs, preemptible VMs, just for encoding pods there. And that on the same Kubernetes cluster, we can have a different node pool with 4 CPUs machine, only for running our API pod. So this integration is very powerful because you can use the right hardware for the right job. And this, in the end, saves money. Another cool thing we use on Kubernetes is, of course, the Kubernetes horizontal pod outscaling. This means that Kubernetes has the ability to increase and decrease the number of pods automatically when it's needed. In our case, our API, in the morning, we have less people using it. So Kubernetes, it's automatically keeps the amount of pods running at the minimal level. However, in the afternoon, in the evening, when we have more people watching our channel, more traffic arriving, Kubernetes can detect it and automatically increase the amount of pods. So our platform is ready for this new data, right, for this new traffic. And we can still keep replying in the prime. As soon as Kubernetes realizes these resources is no longer needed, it will automatically decrease your platform down. So this also saves money for you, because you don't need to run more resources than what is really needed on that moment. Yeah. Other big problem we had was about the storage. And the Google Nearline storage, it really solves all the problems we had. It's a great speed cost benefit. You can retrieve data faster in like around 1 second. Costs only around 10 euros per month for terabyte. And this is really midfield between a regular storage and the disk attached straight away to your machine. Because it works fast, we can even play some previews of 4K video to our office straight away from the storage. When we start, I didn't imagine this could be possible, but it works pretty good, actually. So the main question, $1 million question, was it all worth it? Yes, it was. If your company is thinking about migrating to Kubernetes, you should start it right now. It has great benefits, of course, a bit of work to get it done, and Google Cloud Platform really helps you to deploy it. So now, right now, we have our main applications running already on Kubernetes. No longer we need this in-house infra, thanks God. And we can encode the machines with preemptible, very fast and efficient for us. It's cheap. Actually, it's 15 times faster now, the encoding process, than what it was in-house. And the preemptibles make it's really affordable. And the nearline storage on Google really fixes all problems related to storage capacity and electric outage. We don't have anything of that anymore, of course. And the most important aspect, reliability. We can trust, we can rely more on our software that it's going to work, because we have no longer hardware issues or electric issues. So it works way better than before. What's next for us at Excite? Well, Excite is growing very fast. We're going to be probably in 25 different countries in the next 2 or 3 years. So of course, I want to federate everything. I want all my clusters that I'm going to release on different zones around the world to connect, to integrate, to put my customers to talk to each other if needed. And another thing that we are missing a bit on Kubernetes, and I have good news that we're going to have before in a bit from James, it's a STO. It's a SASE mesh system that we're going to need. Matt talked about a bit about it, and I'm looking forward to implement it. It's important for us at Excite to keep using top technologies, and STO, I do believe, is the next new thing coming, and this will be a really game-changer for Kubernetes clusters. Well, if you have any question, this was it for me. I will be around. It will be great to talk to you about Excite, Kubernetes, or anything on Google Cloud Platform. Thank you very much for coming, and this was it. Thank you, guys. Thank you, James.
Thank you, Igo. So I know many of you are probably getting hungry, and it's going to get a little bit nerdy from this point onwards, so try to keep your brains running for a little bit longer. So let's talk about using capacity efficiently for a moment. So many people in the room might be familiar with the feeling of having a few processors, say, running on a VM or a few VMs, and it doesn't feel logical to put some other processors there, so you leave it like that, but the VM's largely idling. The machine, is not using all of the memory and CPU available to it. Well, the Kubernetes scheduler is really good at playing Tetris. I think that's a good way to think about it. It knows how to pack those containers into the available capacity really efficiently. And I've heard it said that you could even quadruple the effective capacity of your data center in this way. But for some people, that's not enough. So let's talk about how you could run a 5,000 node cluster. So maybe there's someone in the room who would like to run a 5,000 node cluster. I've definitely got colleagues who would be interested in talking to you afterwards. So if you ran a 5,000 node cluster and you used our 64 core machines, which have launched quite recently, I think you would have 233,600,000 core hours per month. And you'd be paying about $7 million a month for that. But once the sustained use discount kicked in, I think you'd get it down to under $4 million. But obviously not everybody wants to do that. The good news, though, is that because we operate clusters at scales like that, everyone benefits in terms of latency. So we have design targets that our APIs, the Kubernetes APIs, should respond in under 1 second, and that pods should start up within 5 seconds. So Igo mentioned federation. If you wanted to have the ultimate high availability solution, you could run a cluster in each region where you had customers around the world and get them to join a club, which is called a federation, and get some sort of centralized control over the components in it. And at the same time, you could have a single global load balancer in front of it, which would automatically take care of routing your client's requests to the nearest healthy cluster in the world. So as your clusters grow and your operations teams grow, you probably need to think about how you're going to control access to all of these things. All your eggs could be in one basket now otherwise. So in the past, here we have a blue team and a green team. If these people had access to the cluster to change things, then that was it. They could do what they liked. Then along came namespaces, which gave us some form of separation, but not really enforced with teeth. So you could separate out your concerns here, but you couldn't. You could just do things like, say, the blue team will get a certain amount of CPU and memory, and the green team will get the rest. But now, with role-based access control, that can be enforced. So if you have a user, a group, or a service account, and a resource that you want to control access to, and a resource doesn't just have to be a namespace. Here we have that as an example. It could be a pod, or it could even be, say, read access to the logs that that pod writes. Now, you can have a role, which will play a part in connecting those things together. So a role could be an out-of-the-box role. So cluster admin, right the way down to somebody, a custom role of somebody who could write or read a particular resource, or even a combination of resources. And you can connect them together with a role binding, giving you that fine-grained access control. Another thing is storage. So earlier we talked about disconnecting from the physical world and just thinking about our application and our service-centric view of the world. Unfortunately, storage seems to take us back to that physical world. And people may be familiar with the days when they had to request storage, say their server or their cluster was running low and panicking about the database, causing it to overflow and crash. You would actually have to request storage. Maybe someone would have to rack it. More recently, someone might separately still, an ops team perhaps, might provision it with your cloud provider. And then they would attach it to a node or a VM, which still doesn't quite fit in with this service-centric view of the world we've been talking about, because your pod might one day be running on one node or VM, and the next day it might be on another. So For a while, we've had persistent volume claims, which give you a means of associating your storage after you've provisioned it with a running pod. Wouldn't it be nice if we could automate that? Well, now we can do that with dynamic provisioning. So if a pod starts up and it has a persistent volume claim and it wants to have this storage associated with it, if it doesn't already have access to the storage, that storage can just be created on the fly. We also have something called storage classes, which is basically a blueprint for a certain type of storage you might have. So different cloud providers or some SSDs, and you can effectively give it a label and make an abstraction there. So say the SSDs are your gold storage or your fast storage. So then all your persistent volume claim has to do is say, I want this kind of storage and I want this amount of it, and it'll get sorted out. So I think we're back in the application-centric view of the world. So we talked about all these high availability features. Now we have some new scheduling challenges as well. So you could run a cluster across multiple availability zones already. And by default, the scheduler will just put the containers in the first free node that it finds, without much regard to where things should be. So you can have some extra use cases. So for instance, you have a legacy service running on a VM in zone C, and you want to run some pods which particularly need to talk to that legacy service. I think you might like them to be together because you want to minimize and avoid that little bit of latency that comes with talking in between zones, and some small costs as well. Or you might be like Ego, and you might have a special node pool with special hardware for video encoding. And you want your pods to run in that node pool. Well, now we have extra control over that with something called node affinity. So in this case, we have our legacy service running in zone C, and we want to schedule a pod next to it. And we can configure that in something like this. Now, I know this looks like YAML on a slide, and lunch is nearly here, but it's a bit like poetry, I think. If you keep saying, required during scheduling, ignored during execution, there's something wonderful about that. And I think if you think about what that means, it means that here we've got something like a key and a value. So we're saying that our key is our failure domain, in this case a zone. And we want our pod to be landing in zone C here. And we actually require that. So that is a strong requirement. We could also say that we prefer during scheduling, ignore during execution. And unlike node selector, we get these extra operators, including some exclusive operators that would let us repel workloads from that particular key. And some standard keys. So we have failure domains, zone and region, host name, and you can have custom things, also preemptables, SSDs, that sort of thing. So that gives us some control there. But there are other use cases that maybe node affinity doesn't help you with so well. So say you have a front-end service and a back-end service, and you want them to land together, again, to minimize latency. They're talking to each other all the time, but they're not actually in the same pod. So these two processes ideally are in the same availability zone as well. That's something that we call north-south communication. And you don't want to have to say they have to be in zone B or zone C. You just want them to be in the same availability zone. So that's something where you can achieve with interpod affinity. Here it is again, required during scheduling, ignored during execution. So again, we have a topology key. In this case, we just say that's the zone. And we have an operator, which is in, and we're saying that our back end should land in the same zone as our front end. We could say preferred during scheduling, ignored during execution. And in this case, we could also say what happens at execution is important as well. So say something changes in the cluster topology, everything could move around. So pods that were no longer in the right place because something changed would move to another node. Now, one more quite techie thing, and that's taints and tolerations. So imagine you have one node which has got some special hardware on it, and two regular nodes. So here we've got 3 nodes, and one of them has a couple of GPUs in it. Say, for your use case, you go of video encoding. And here we've got a regular pod, which is just going to do some sort of regular job. It doesn't particularly need a GPU. And it comes along, and the cluster's bare, and it just gets scheduled in the first node that it comes to, and that just happens to be our GPU node, which is a shame because next along comes a GPU pod. So by that I mean a pod that's going to do some work that would really benefit from having access to that GPU. But we could have this scenario now where we've already scheduled something on our GPU node, and it's basically full up. There's no extra capacity there. So either this GPU workload won't get scheduled, or it'll have to go somewhere else. And effectively, our expensive GPU hardware is wasted. Well, we can solve that with something called taints and tolerations. So this is quite simple, really. We can label our GPU node with something called a taint. So it's marked that it has a GPU. And we use this expression, prefer no schedule, which just means it's going to repel everything that comes its way. So it's saying, I don't want any pods, unless when the GPU pod comes along, we've given it something called a toleration. So this pod can tolerate running on a GPU node. So we'll get the happy case where the regular pod has not been scheduled there because it was repelled, because it did not have that toleration. But the pod with the toleration for GPU, the one that wants the GPU, can take the slot. And now we end up in this happy scenario. Now, imagine, because we say prefer no schedule, imagine the case where our regular pods have already filled up all of the available capacity, and the only place left to schedule something is on the pod which has the GPU. Well, that can happen because of that preference, so it's a loose constraint. So how many people in the audience, hold up your hand if you've heard of this concept of an SRE, a site reliability engineer. So that's something we believe in a lot at Google. We literally wrote the book on site reliability engineering. It's a major contribution we made to the DevOps culture, I would say. Well, we want to be your SRE too. So Ego talked about how Google takes care of managing your control plane for you. This takes away a lot of the pain. So routine ops-like stuff you have to do, like handling backups, monitoring, repairing the control plane should something go wrong in the availability zone or wherever it is, the physical hardware. Well, in this case, it's container engine, so the availability zone. We take care of keeping it healthy, and we can resize that control plane for larger clusters. And we aim to keep it running for you all of the time. And we also look after the components on your nodes, so the Kubernetes components. So we give you things like logging with Stackdriver, integrated with Stackdriver, monitoring, metrics. We pre-install the components needed to act as a backend for our global load balancer. And now, with 1.6, we can manage your nodes too. So we can handle operating system updates, security patches, Kubernetes upgrades seamlessly. And if there's a problem with the kernel of a VM, or it's out of memory, or something else is detected, we can also drain the pods that are running on there, if we can, and restart that node and bring up another one to replace it. So you don't have to think about that kind of thing. And so that you can keep track of all of that, we have a full audit trail. So you can tell whether it was someone from your team or the robot that took those actions on your behalf. So what's next? Well, in 1.7, we've got another release coming. They come every 3 months, and they're pretty much bang on time all of the time. We're going to have better support for GPUs, which is now a feature you can have on Google Compute Engine and Container Engine. We're going to do more to keep your secrets secret, so you can integrate with something like Google Certificate Manager or HashiCorp Vault to store the secrets that your services might use to talk to each other or things in the outside world. We're going to have IP virtual switch load balancing, so that's a bit faster than the existing built-in load balancing using IP tables. We're going to make it easier for add-ons to integrate with the core Kubernetes API. And it's going to be possible to upgrade the components of Kubernetes on a running cluster more easily. And this is the thing, Matt mentioned it earlier, the thing that I'm most excited about at the moment, because I'm really interested in microservices. And there are still challenges with microservices. So you hear the story all the time about how people are breaking their monoliths down into into microservices. But it does bring some complexity. Most successful microservice stories started in that way, breaking down some existing thing into a monolith. And every developer at least, is probably familiar with dealing with concerns like, how do I handle an HTTP failure? How do I do HTTP retries and exponential backoff and that kind of thing, perhaps in 5 languages? How do I handle rate limiting or internal load balancing in between my services? How do those services really discover each other? People are introducing all sorts of additional frameworks for service discovery. Why should my application have to think about its own encryption when that could just be handled by something at the network level, a service mesh? And Istio brings you all of those things. So it's something that's completely open source. It's been designed to run on any platform, any environment. But first of all, it's running on Kubernetes. It's an effort from the community, so Google are obviously involved. IBM and Lyft brought their Envoy proxy, which is a super fast, it was already open source, C++, layer 7 proxy load balancer, which automatically gets injected next to your pods, picks up the traffic, and can handle all kinds of great things like the things I mentioned before, even canary releasing or directing traffic that's activated, that comes from a particular person to a particular backend or version of your service. And you can try it out today. So I think with just a couple of commands, you could install it in a Kubernetes cluster running locally or on Container Engine. And there are some great tutorials on the website. If you go to the tasks there, you can get running with canary releasing and user-specific sort of A/B testing and things like that more or less straight away. So please have a look at istio.io. And if you're not already playing with a Kubernetes cluster, you can do that on your laptop. So you could try all of the features I've talked about today by installing Minikube, which is represented by the first logo. It's one command to install it on a laptop, and you have a running single node, obviously, cluster. Or you could take advantage of Google Container Engine and our free pricing tier, so you get $300 a month. And you could run a multi-node cluster for quite a while on Google Container Engine and try out all of these things like multi-availability zones. And have a look at Istio, because I think it's really cool. I'll be down here at the front immediately afterwards and then out in the hall. So if you have any questions, please just come up to me and ask. And thank you very much.